right, calculus students, Ms. Deer back on the mic here. Gonna go through some seriously, with you today. So we started out with the idea of a positive series. So the first thing we want to ask ourselves is it geometric? Is it telescoping? If so, we can actually find the sum of the series. Does it pass the nth term test? Do the terms go to 0? If not, it diverges and we're done. Is it a p-series, which is the form 1 over n to the power of p? If p is 1, this is our harmonic series, which we know diverges. If p is greater than 1, it converges. If p is less than 1 but greater than 0, it diverges. Then we ask ourselves, is it almost a p-series and almost a geometric series? We use direct comparison. Remember, if we're smaller than something that converges, this also converges. If we're bigger than something that diverges, our series also diverges. If we're bigger than something that diverges, if we're bigger than something that converges, it doesn't really tell us anything, and we are left with limit comparison. After limit comparison, integral test. Then we introduce the idea of alternating series. An alternating series, again, take out the alternating piece. So we either have -1 to the n times an or -1 to the n plus 1 times an. This first term is positive because the first term is -1 squared. This first term is negative because it's -1 to the 1. All we need to show that these converge is that the limit as n approaches infinity of the non-alternating part goes to 0, it converges. Then we have to decide, does it converge absolutely or conditionally? Then we introduce the idea of two tests that either converge absolutely or they diverge. So we have the ratio test, which says the ratio of the next term to the previous term. This is really good when we have factorials or exponents. And then we have the nth root test. For both of these, if the limit as n approaches infinity, here of the ratio, here of the nth root, if the limit as n approaches infinity is less than 1, it converges, greater than 1, it diverges, and if the limit is 1, inconclusive. We have to try another test. All right, so I'm going to look at some examples here with you. So let's look at the sum from n equals 1 to infinity of n squared 2 to the n over 5 to the n plus 3. Now I have some exponents. I also have some polynomials. I don't want to do my nth term test, so this is a good time for the ratio test. So if I take the limit as n approaches infinity of the n plus 1, so every time I see an n, I'm going to plug in an n plus 1, 2 to the n plus 1, over 5 to the n plus 1 plus 3, divided by my original, so multiply by the reciprocal, I get 5 to the n plus 3 over n squared 2 to the n. Now again, this is a little different than the limits we've been doing. We don't want to L'Hopital this, we just want to look at the similar terms. So 2 to the n plus 1 over 2 to the n leaves an extra 2 on the top. 5 to the n plus 3 over 5 to the n plus 4 leaves an extra 5 on the bottom. N plus 1 squared and n squared, we know that limit is 1. So this whole limit is 2/5, which is less than 1. So this converges. Let's try another one. Let's take the sum from n equals 1 to infinity of, let's do 3 to the n over 2n factorial. So again, I have the factorial in here, which makes us think that we want to try the ratio test. So when I take the limit as n approaches infinity, I'm going to do 3 to the n plus 1 over, now when I add 1, I don't just add 1 on the n. This is 2 times n plus 1, all factorial, times 2n factorial over 3 to the n. We can see this is going to leave me an extra 3 on the top. But here, what I have, this 2 distributes. So I get 2n plus 2 factorial, which becomes 2n plus 2, 2n plus 1, times 2n factorial. So these cancel, and I get the limit as n approaches infinity. Again, I had a 3 left on the top. 3 over 2n plus 2 times 2n plus 1, which is 0. 0 is definitely less than 1, so this converges. Now the ratio test converges absolutely, but because this is not an alternating series, it just converges. So let's take a look at another one. Let's say I have the sum from n equals 1 to infinity of n plus 4 over 2n minus 1. Well, right away, we see that the limit as n approaches infinity of n plus 4 over 2n minus 1 is 1/2, not 0, so it diverges. Nth term test. So satisfying. Let's take the sum from n equals 1 to infinity of 3 over negative 2 to the n. This is a geometric converging series, but it starts at 1, so we can rewrite it as the sum from n equals 0 to infinity. Our first term, if we plug in 1, is negative 3/2. And then, so this is our a, and our ratio every time is negative 1/2 to the n. So it converges to a over 1 minus r. Negative 3/2 divided by 3/2 is negative 1. Let's take the sum from n equals 1 to infinity of 2n plus 1 over 3n minus 2, all to the nth power. Well, whenever we see this, we know we want to nth root it. So if we look at the limit as n approaches infinity of the nth root of something to the nth power, we just get 2n plus 1 over 3n minus 2, which is 2/3. Now here, unlike when we're using the nth term test, 2/3 is less than 1, so this converges by the nth root test. The sum from n equals 1 to infinity of 1 over n squared plus 8. Well, this is almost 1 over n squared. So if we compare it to 1 over n squared, this is smaller because the denominator is bigger. So this converges by direct comparison. Let's do a couple more. Let's say I have the sum from n equals 1 to infinity of negative 1 to the n over n squared plus 8. Well, now it's alternating. Is the not alternating piece going to 0? Yeah, so this converges. And we just showed that 1 over n squared plus 8 converges by comparison to 1 over n squared. So because both the alternating series and the not alternating series converge? We say that this series converges. Absolutely. How about if we take the sum from n equals 1 to infinity of 3 to the n over 2 to the n? Well, we could certainly nth root this and write it as 3 over 2 to the n. But when we do that, hopefully we notice that this is actually a geometric series, and r is 3/2, which is too big, so it diverges. If I were to use the nth root, it also diverges because the limit as n approaches infinity of 3 over 2 is 3 over 2, which is too big. So if you don't spot the geometric series